Right now, at this very moment, a rock the size of the Empire State Building is hurtling through space at roughly 63,000 miles per hour. It has been traveling like this for billions of years, looping around the Sun in a path that brings it dangerously close to Earth every 6 years. Its name is Bennu, and in the year 2182, there is a chance, a real, calculated, scientifically verified chance, that it will slam into our planet with the force of more than 1 billion tons of TNT. That is not a Hollywood pitch. That is not a thought experiment designed to make a YouTube thumbnail more clickable. That is a number produced by the most precise orbital tracking system ever built by human beings. NASA has measured Bennu's trajectory with a margin of error smaller than the length of a football field across a distance of tens of millions of miles. And after running those numbers through thousands upon thousands of simulations, the conclusion is quiet, clinical, and deeply unsettling. There is approximately a 1 in 2,700 chance that Bennu will hit Earth on September 24, 2182. 1 in 2,700. That might sound small. It might sound like something you can safely ignore. But consider this thought experiment for a moment. If someone handed you a bag containing 2,700 marbles, 2,699 of them white, and one of them black, and told you that drawing the black marble meant the obliteration of a city the size of Paris, would you reach in? Would you shrug it off and say probably fine? Would you go back to sleep? Because that is what the human race is doing right now. We know where the marble is. We can see the bag. We have measured the odds with extraordinary precision. And yet, for most people on this planet, Bennu is just a name they have never heard. Now picture the impact itself. An object 500 meters across, wider than the length of 5 football fields, placed end to end, strikes the surface of the Earth at roughly 12.5 kilometers per second. That is almost 38 times the speed of sound. The energy released upon impact is roughly 1,200 megatons of TNT. That is 24,000 times the energy of the bomb that leveled Hiroshima. The initial blast would excavate a crater more than 5 kilometers wide and nearly a kilometer deep. Everything within a 50-kilometer radius would be incinerated instantly. The shockwave, expanding outward at supersonic speed, would flatten structures across an area larger than some European countries. If the impact were in the ocean, and the ocean covers 70% of the Earth's surface, making a water impact statistically more likely, the resulting tsunami could reach heights of tens of meters and strike coastlines thousands of kilometers away within hours. The dust and debris lofted into the upper atmosphere would dim sunlight across an entire hemisphere. Crops would fail across multiple continents. Temperatures would drop by several degrees for months, possibly years. The economic toll would be measured in the trillions of dollars. The human toll could be measured in millions of lives. And this is not even the worst-case scenario. This is the moderate estimate, produced by scientists who are careful with their language and conservative with their numbers. The actual devastation would depend on where it hits, land or sea, populated or remote, equator or pole, and on factors we cannot predict in advance. Here is what makes this story different from every other asteroid scare you have ever read about. We did not just spot Bennu through a telescope and calculate its orbit from a distance. We went there. In 2016, NASA launched a spacecraft called OSIRIS-REx, a machine roughly the size of a large van, weighing about 2,100 kilograms, and sent it across the void of space to rendezvous with this asteroid. It arrived in December of 2018. For more than 2 years, it orbited Bennu, photographed every boulder on its surface, measured its mass with extraordinary precision, mapped its gravity field, and analyzed its chemical composition down to the molecular level. And then, in 2020, it did something that had never been done before in the history of American space exploration. It reached down, touched the surface of the asteroid, and grabbed a sample, actual physical material, ancient rock and dust, from an object that might one day collide with our world. That sample, roughly 250 grams of primordial material, arrived on Earth in September of 2023. Scientists at NASA's Johnson Space Center have been studying it ever since, using instruments sensitive enough to detect individual atoms, What they found inside was not what anyone expected. It was not just inert rubble. The sample contained water, not liquid water, but water molecules locked into the crystal structure of the minerals, evidence that Bennu's parent body once harbored liquid water in its interior. It contained organic molecules, complex carbon-bearing compounds, including amino acids, the building blocks of proteins, and ultimately of life. And it contained minerals that have never been found on Earth in their pure, unaltered form. Minerals that crystallized in conditions that no longer exist anywhere in the inner solar system, conditions that disappeared billions of years ago. Bennu is not just a threat. It is a time capsule from the very birth of the solar system, 4.6 billion years old, carrying secrets about how planets formed, how water was delivered to a young and barren Earth, and perhaps even how the chemistry of life itself was first assembled in the darkness between the stars. And therein lies the paradox that makes this story unlike any other in the history of science. The same object that might one day end a city could also hold the answer to how life started. Destruction and creation, apocalypse and genesis, wrapped together in a single boulder-covered rock, spinning silently through the dark. By the end of tonight, you are going to understand exactly what Bennu is, where it came from, why it is heading toward us, and what, if anything, humanity can do about it. You are going to learn about the invisible force that is quietly pushing this asteroid toward a collision course with Earth, a force so subtle that it took decades for scientists to even confirm it existed. You are going to meet the scientists who risked a 200 million mile journey to grab a handful of dust from the surface of one of the most dangerous objects in the solar system, and who discovered things about the origins of our world that no one had dared to imagine. And you are going to confront a question that most people would rather not think about. A question that sits at the intersection of physics, probability, and human survival. What happens if the black marble gets drawn? This is a story about time, deep time, geological time, the kind of time that stretches so far into the future that the people who will face Bennu's closest approach have not been born yet, and their grandparents have not been born yet either. It is a story about precision and uncertainty, about how the most powerful computers on Earth can model the trajectories of thousands of asteroids simultaneously and still be unable to answer the simplest question with confidence. Will this one hit us? And it is a story about what it means to be a species that can see a danger coming from more than 150 years away, but might lack the collective will to do anything about it until the threat is too close to ignore. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. To understand why Bennu matters, you first have to understand what an asteroid actually is, and more importantly, what it is not. Most people picture asteroids as smooth, round rocks drifting lazily through space, like the polished stones you might skip across a lake. That image, the one reinforced by decades of science fiction movies and low-budget television specials, is almost entirely wrong. Real asteroids are jagged. They are ancient beyond comprehension. And many of them, including the one we are talking about tonight, are not solid objects at all. They are rubble piles. Loose, fragile collections of rock, dust, gravel, and void, held together by nothing more than their own feeble gravity, and a mysterious set of cohesive forces that scientists are still struggling to fully understand. They are not boulders. They are sandcastles, barely holding their shape in the vacuum of space. Remnants of a construction project that was abandoned 4.5 billion years ago when the solar system was still deciding what it wanted to be. Bennu is one of these rubble piles. It is roughly 500 meters across at its widest point. A little taller than the Empire State Building, a little wider than the length of 5 football fields laid end to end. Its shape is unusual. It is not a sphere. It is not an elongated potato, like many asteroids. It is shaped like a spinning top, a diamond or a rhombus, wider at the equator than at the poles, with a pronounced ridge running around its midsection like a belt pulled too tight. This shape is a clue to its history, a signature of the forces that have been acting on it for millions of years, and we will return to it later. If you could somehow stand on Bennu's surface and look around, You would not see a smooth landscape. You would see chaos, enormous boulders, some the size of houses, some the size of apartment buildings, jutting out at sharp angles from fields of broken rubble, fine gravel and dust coating every crevice and hollow, deep, pitch-black shadows cast by rocks that have not moved in millions of years, because there is no wind, no rain, no erosion of any kind, only the slow, patient grinding of micrometeorite impacts, and the relentless thermal cycling of day and night. And beneath your feet, a surface so loosely packed that you might sink into it if you shifted your weight too quickly. The gravity on Bennu is almost non-existent. It is roughly 100,000th of what you feel standing on the surface of the Earth. If you weigh 80 kilograms on Earth, about 176 pounds, you would weigh less than a gram on Bennu, less than the weight of a paperclip. If you jumped with the force of a normal step, you would not come back down for hours. You might not come back down at all. A moderate leap could launch you clear of the asteroid's gravitational hold entirely, sending you drifting gently into open space, watching Bennu shrink to a dark speck behind you as you floated away with absolutely no way to stop or return. The asteroid's escape velocity, the speed you would need to reach to leave its gravity forever, is roughly 20 centimeters per second. That is less than half a mile per hour. A casual toss of a baseball would send the ball into orbit around the Sun. This is the object that could one day impact our planet, an object so fragile that an astronaut could not safely walk on it, an object so dark that it reflects only about 4% of the sunlight that hits it. Darker than fresh asphalt, darker than charcoal, one of the darkest objects ever visited by a spacecraft. An object that weighs roughly 78 billion kilograms, which sounds like an enormous number, but represents less than 1/1000th of the Earth's mass. If the Earth were a bowling ball, Bennu would not even be a grain of sand. It would be a speck of dust, invisible without a microscope. And yet, that speck of dust, moving at 12.5 kilometers per second, carries enough kinetic energy to reshape a continent. The story of how we found Bennu begins not with cutting-edge space telescopes or billion-dollar satellites, but with a simple nagging fear. In the 1980s and early 1990s, a small group of astronomers began asking a question that most of their colleagues considered premature, alarmist, or simply absurd. What if an asteroid were heading for Earth right now? Would we even know? The answer at the time was almost certainly no. The technology to systematically detect small, dark objects moving through the inner solar system did not exist in any comprehensive form. We could find the big ones, the civilization enders, objects a kilometer or wider, the kind of rock that killed the dinosaurs 66 million years ago, when a roughly 10-kilometer impactor struck what is now the Yucatan Peninsula in Mexico, triggering a global extinction that wiped out 75% of all species on Earth. We had found many of those large objects, and none of them were on a collision course. But objects in the range of a few hundred meters? Those were invisible to existing surveys, and a few hundred meters is more than enough to flatten a major metropolitan area, devastate a coastline, and alter the global climate for years. This fear was not purely theoretical. It was anchored in an event that had actually happened. An event that should have terrified the world, but was instead largely forgotten for decades. Buried in the dense taiga forests of central Siberia, on the morning of June 30th, 1908, something streaked across the sky above the Tunguska River region in remote Siberia. Eyewitnesses, scattered reindeer herders and traders, the only humans in the area, reported a column of blue-white light brighter than the sun, followed by an explosion so powerful that it knocked people off their feet more than 60 kilometers from the blast center. The shockwave flattened roughly 80 million trees across an area of more than 2,000 square kilometers, an area larger than the entirety of Greater London. Barometric sensors in England, more than 5,000 kilometers away, detected the pressure change. Seismographs across Europe recorded the tremor as if a moderately powerful earthquake had occurred. For several nights afterward, the skies over northern Europe and Central Asia glowed, with an eerie luminescence so bright that residents of London and Stockholm could read newspapers outdoors at midnight without any artificial light. And yet, whatever caused the explosion left no crater. No fragment of cosmic rock was recovered from the blast zone. No obvious remnant of the impacting body was found. It was as though the sky itself had detonated. It took decades for scientists to reach a consensus on what had happened. The leading explanation, supported by the pattern of fallen trees and the absence of a crater, is that a small asteroid or comet fragment, perhaps 60 to 80 meters across, no larger than a modest apartment building, entered the atmosphere at a steep angle and at a speed of roughly 15 to 20 kilometers per second. The enormous friction and pressure of atmospheric entry heated the object to tens of thousands of degrees and compressed the air ahead of it into a superheated shockwave. The object never reached the ground. Instead, it broke apart and exploded at an altitude of roughly 5 to 10 kilometers above the surface, releasing energy estimated at between 10 and 15 megatons of TNT. To put that in perspective, 15 megatons is 1,000 times the energy of the atomic bomb dropped on Hiroshima. It is roughly the yield of the most powerful nuclear weapon ever tested by the United States. The Castle Bravo shot at Bikini Atoll in 1954, and the object that produced this almost inconceivable devastation was small enough to fit comfortably inside a soccer stadium. It was nothing, cosmically speaking, a pebble, a mote, a tiny fleck of debris left over from the formation of the solar system, and it very nearly rewrote the history of an entire region. The Tunguska event was a warning shot, a cosmic reminder that Earth exists in a shooting gallery, but because it occurred in one of the most remote regions on the planet, with no cities or towns in the immediate blast zone, and because it happened in 1908, before the age of instant global communication, the lesson was slow to arrive. For most of the 20th century, asteroid impacts were treated as a topic for science fiction writers, not serious scientists. The prevailing view in the astronomical community was that Earth impacts were rare events separated by millions of years, and that worrying about them was about as productive as worrying about the sun exploding. That attitude began to change in the 1980s, driven by two developments that transformed planetary science. The first was the discovery by physicist Luis Alvarez and his geologist son Walter Alvarez that the mass extinction at the end of the Cretaceous period, the event that killed the dinosaurs, was caused by an asteroid impact. Their 1980 paper, which identified a thin layer of the element iridium in rock formations worldwide at the boundary between the Cretaceous and Paleogene periods, provided the first hard physical evidence that impacts from space could cause global catastrophes. The iridium, an element rare on Earth's surface but abundant in asteroids, was the smoking gun. It was everywhere, at exactly the right geological layer, in exactly the right concentration. Something very large had struck the Earth 66 million years ago, and everything had changed afterward. The second development was the realization, driven by improving telescopic surveys, that near-Earth objects were far more numerous than anyone had previously believed. By the early 1990s, the catalogue of known near-Earth asteroids was growing rapidly, and it was becoming clear that the inner solar system was not the orderly, emptied-out region that textbooks described. It was full of small, dark, fast-moving objects on orbits that crossed the paths of the terrestrial planets. Some of them had already come uncomfortably close to Earth, without being detected until after the closest approach, appearing first in telescopic images taken after the fact, like surveillance footage reviewed after a crime. It was this growing awareness, the combination of the Alvarez discovery and the expanding asteroid catalogue, that led to the creation of dedicated search programs. In 1998, the United States Congress directed NASA to find and catalogue 90% of all near-Earth objects larger than 1 kilometer within 10 years. The program was called the Spaceguard Survey, a name borrowed from a passage in Arthur C. Clarke's science fiction novel Rendezvous with Rama, and it marked the first time in human history that a civilization had formally, officially decided to watch the sky for incoming threats. The search programs were remarkably productive. Using ground-based telescopes equipped with sensitive digital cameras and automated detection software, teams of astronomers methodically scanned the night sky night after night, cataloguing every moving dot of light. LINEAR, the Lincoln Near-Earth Asteroid Research Program, operated by MIT's Lincoln Laboratory at a site near Socorro, New Mexico became one of the most prolific asteroid discovery engines in the world. Other programs joined the effort: the Catalina Sky Survey, operating from telescopes in Arizona, the Spacewatch project at Kitt Peak, Pan-STARRS, a wide-field survey telescope on the summit of Haleakala in Maui, Hawaii. Between them, they found thousands of previously unknown near-Earth objects within the first decade. Most of these discoveries were scientifically interesting, but posed no threat. Rocks on orbits that would not bring them dangerously close to Earth for millions of years, if ever. But a few stood out. A few followed paths that crossed Earth's orbit at uncomfortably close range. A few were large enough and close enough to warrant careful monitoring. In 1999, on a September evening in the New Mexico desert, the Linear Telescope captured a faint dot of light moving against the fixed pattern of background stars. It was small, dim, and relatively fast, characteristics that suggested it was close to Earth and orbiting the Sun on a path that kept it in the inner solar system. The astronomers recorded its position, submitted the data to the Minor Planet Center in Cambridge, Massachusetts, the global clearinghouse for asteroid observations maintained by the International Astronomical Union, and moved on to the next dot. It was designated 1999 RQ36, a string of alphanumeric characters, cold and institutional, that told you nothing about the object's significance or the role it would come to play in the story of planetary defense. That clinical designation would later be replaced by a name drawn from ancient Egyptian mythology. Bennu, the heron-shaped deity associated with the sun, with creation, with rebirth. In Egyptian cosmology, the Bennu bird was connected to the cycles of death and renewal, to the flooding of the Nile, and to the first sunrise at the beginning of time. The name was proposed by a 9-year-old boy from North Carolina named Michael Puzio, who entered a naming contest run by the OSIRIS-REx mission team and the Planetary Society in 2013. Michael thought spacecraft, with its long robotic sampling arm extended and its twin solar panels spread wide, looked like the mythological heron reaching down to touch the primordial waters of creation. The judges were charmed by the image and selected the name. And so a 4.6 billion-year-old rock, born in the violent formation of the solar system and now hurtling through space on a potential collision course with its planet of origin, was named after a god of renewal, a deity whose mythological role was to carry the souls of the dead into the afterlife and to bring new life from the ashes of destruction. The irony of that name would deepen with every passing year of study. But before the name, before the mission, before anyone realized the full extent of the threat, Bennu was just another dot in a growing catalogue of potentially hazardous objects. The early observations were sparse. A handful of position measurements over a few weeks in 1999. Barely enough to determine a rough orbit. Bennu was then lost in the sun's glare, as its orbit carried it to a part of the sky too close to the sun to observe. It would not be recovered until 2005, when astronomers picked it up again and added new data points to the orbital fit. With the additional observations, the orbit became clearer and more worrying. Preliminary impact analyses, run by both NASA's Sentry system at the Jet Propulsion Laboratory and the European Space Agency's NEODIS system in Pisa, Italy, flagged Bennu as an object with a non-trivial probability of future Earth impact. The probabilities were small, fractions of a percent, but they were persistent. They did not go to zero as more data came in, the way they do for most newly discovered asteroids. Usually, when an asteroid is first discovered and its orbit is poorly constrained, the uncertainty region is large, and there may be a statistical chance of impact. But as more observations narrow the orbit, the uncertainty shrinks, and the Earth typically falls outside the revised prediction. The probability drops to zero, the asteroid is declared safe, and the scientists move on. For Bennu, this did not happen. Each new observation refined the orbit, but the refined orbit kept threading a needle, kept passing close enough to future Earth positions that a small but stubborn impact probability remained. This stubborn persistence caught the attention of the planetary science community. Bennu was not just another near-Earth asteroid. It was a test case for the limits of orbital prediction. It was a reminder that some asteroids cannot be declared safe or dangerous from ground-based observations alone. because the forces acting on them, particularly the Yarkovsky effect, introduce uncertainties that telescopes and radar simply cannot resolve from a distance of millions of kilometers. It was this realization that made Bennu the ideal target for a sample return mission. In 2004, a team led by planetary scientist Dante Lauretta at the University of Arizona began developing a mission concept that would later become OSIRIS-REx. The proposal was ambitious: visit a near-Earth asteroid, study it in detail, collect a sample, and return it to Earth. Several candidate asteroids were considered. The selection criteria were demanding. The asteroid had to be accessible, on an orbit reachable by a spacecraft launched from Earth with existing rocket technology. It had to be large enough to have a meaningful gravity field for orbital operations, but not so large that it would be geologically boring, a featureless, monotonous ball of ancient rock. It had to be carbon-rich, a type of asteroid called a B-type or C-type, because these primitive bodies are believed to preserve the original chemistry of the early solar system. And, ideally, it had to be one that posed a potential impact hazard, so that the mission could serve double duty, advancing both planetary science and planetary defense. Bennu checked every box. It was accessible, it was carbon-rich, it was the right size, and it was one of the most potentially hazardous asteroids known. The mission was selected by NASA in 2011 as part of its New Frontiers program, the same program that funded the Juno mission to Jupiter and the New Horizons flyby of Pluto. The total cost, including development, launch, operations, and sample analysis, would eventually reach more than $1 billion. It was one of the most expensive planetary science missions ever flown, but the potential payoff, in terms of both science and survival, was incalculable. Within a few years of its discovery, follow-up observations revealed Bennu's orbit in increasingly precise and increasingly alarming detail. Radar observations from the Goldstone Deep Space Communications Complex in California and the Arecibo Observatory in Puerto Rico measured the asteroid's distance and velocity with extraordinary accuracy. Optical telescopes tracked its position against the stars over multiple orbits, and from these measurements, orbital dynamicists calculated a trajectory that told a clear and unsettling story. Bennu travels in an elliptical orbit around the Sun, completing one full revolutions every 1.2 years, roughly 437 days. Its orbit is tilted by about 6 degrees relative to the plane of Earth's orbit, and it ranges from a closest approach to the Sun of roughly 0.8 astronomical units, 80% of the Earth's distance from the Sun, to a farthest point of about 1.36 astronomical units. This means Bennu's orbit is very nearly Earth's orbit. It is not a distant, abstract threat lurking in the outer solar system. It is a neighbor orbiting in our backyard, crossing our path at regular intervals. At its closest approach to Earth, Bennu passes within roughly 300,000 kilometers, less than the distance to the Moon. In the cosmic scheme of things, this is absurdly, terrifyingly close. If you shrank the solar system down so that the Sun were a basketball sitting in the center of a gymnasium, Bennu would pass within a fraction of a millimeter of the Earth. They would practically be touching. In the scale of the cosmos, Earth and Bennu are dancing partners, circling each other in a gravitational waltz that has been going on for thousands of years and will continue for thousands more. But proximity alone does not make an asteroid dangerous. What makes Bennu dangerous is the specific geometry of its orbit, the way the orbit is slowly evolving over time, and the forces, both gravitational and non-gravitational, that are gradually reshaping its trajectory in ways that bring it closer and closer to a potential impact. To understand those forces, you need to understand a concept that sounds simple but hides enormous complexity: the Yarkovsky effect, named after a Polish-Russian civil engineer who first imagined it in the 1890s. It is a force so weak that it would take billions of years to move a parked car even a single meter. But in the frictionless vacuum of space, acting on an object for centuries without interruption, it can redirect an asteroid by thousands of kilometers. It is the invisible hand that is slowly, patiently, almost imperceptibly nudging Bennu toward us. And it is the single most important factor in determining whether the 1 in 2,700 odds go up or go down. Ivan Osipovich Yarkovsky was not an astronomer. He was a civil engineer who built bridges and railways in the Russian Empire at the end of the 19th century. But he was a curious man, a man who liked to think about physics in his spare time, and one day, we do not know exactly when, because the original publication has been lost, he asked a question that no one else had thought to ask. If the sun heats one side of a small body in space, and that body is spinning, does the asymmetric radiation of heat create a net force? The answer, as he worked it out on paper, was yes. The logic is deceptively simple. One side of the asteroid faces the sun and absorbs sunlight. That energy heats the surface. As the asteroid rotates, the heated surface turns away from the sun and begins to radiate that stored thermal energy back into space as infrared light. But there is a time lag. The surface does not cool down instantly. By the time it reaches maximum temperature, it has rotated past the point directly facing the sun. The result is that the hottest point on the asteroid is not the subsolar point, but a point offset from it in the direction of rotation. The infrared radiation emitted from this hottest point carries a tiny amount of momentum, and because that emission is not pointed directly at the sun, it creates a net force, a minuscule push in a direction that depends on the asteroid's spin. For nearly a century, the Yarkovsky effect was considered a curiosity, a theoretical footnote, too small to measure, too weak to matter. Yarkovsky's original paper was lost. His idea survived only because a few other scientists, notably the Estonian astronomer Ernst Öpik, rediscovered and elaborated on it in the mid-20th century. It was not until the late 1990s and early 2000s, when improvements in radar tracking and orbital modeling made it possible to detect extremely subtle non-gravitational forces acting on real asteroids, that the Yarkovsky effect was finally elevated from a theoretical oddity to a measurable physical reality. The first definitive detection came in 2003, when a team led by Stephen Chesley at NASA's Jet Propulsion Laboratory announced that the asteroid Galevka had drifted roughly 15 kilometers from its predicted gravitational orbit over the course of 12 years. The drift was small in absolute terms. 15 kilometers is nothing compared to the tens of millions of kilometers that Galevka travels in an orbit around the Sun, but it was far too large to be explained by any known gravitational perturbation. The only viable explanation was the Yarkovsky effect, finally caught in the act, confirmed observationally more than 100 years after it was first conceived by an engineer who built railways. For Bennu, the stakes of the Yarkovsky measurement are existential. The force changes the asteroid's velocity by roughly 1/4 of a millimeter per second per year. That is the speed at which a fingernail grows. It is a force so small that it is nearly impossible to visualize in everyday terms. Imagine placing a single sheet of paper on a bathroom scale. The Yarkovsky force on Bennu is weaker than the weight of that sheet of paper by a factor of thousands. And yet, because it acts without interruption, without friction, without resistance, in the perfect frictionless vacuum of interplanetary space, its effects compound year after year, decade after decade, century after century. To put this accumulation in perspective, consider a thought experiment. Imagine you are standing at one end of a football field and you begin walking toward the other end at a pace of 1 step per year. Each step is roughly 1/4 of a millimeter long, invisible to the naked eye. After 10 years, you have moved 2.5 millimeters. After a century, you have moved 2.5 centimeters, about an inch. It seems insignificant. But the Yarkovsky effect does not push position directly, it pushes velocity. And a tiny change in velocity, accumulated over time, leads to a position change that grows quadratically, not linearly, but as the square of the time elapsed. After 150 years, that 1/4 of a millimeter per second annual velocity change translates to a position shift of hundreds of kilometers. Hundreds of kilometers of uncertainty in the predicted location of an object that needs to thread a keyhole less than 1 kilometer wide. The numbers are striking when you lay them out. If Bennu's orbit were governed only by gravity, by the clean, predictable, mathematically solvable equations of Newtonian mechanics, we would know its position in 2182 to within a few kilometers. The gravitational perturbations from other planets are well understood and can be modeled with extreme precision. But the Yarkovsky effect adds an uncertainty that dwarfs the gravitational modeling errors by orders of magnitude. It is, quite literally, the dominant source of unknowing in the most important orbital prediction humanity has ever attempted. And yet, over the 150-odd years between now and the 2182 close approach window, that tiny push shifts Bennu's predicted position by hundreds of kilometers. In a universe where the gravitational keyhole for impact is less than a kilometer wide, hundreds of kilometers of uncertainty is the difference between a confident all clear and a lingering, unresolvable doubt. This is the foundation of the Bennu problem. Not a rock on a fixed course barreling toward Earth. Not a Hollywood scenario where the trajectory is known and the countdown is ticking. Something far more subtle, far more frustrating, and in some ways far more frightening. A rock on a course that is almost but not quite predictable, subject to forces that are almost but not quite measurable, heading toward a date that is almost but not quite beyond the reach of our calculations. An asteroid suspended in the space between knowledge and ignorance, between certainty and chaos, between the calculable and the incalculable. And the only way to narrow that gap, the only way to push back against the ocean of uncertainty that separates us from a definitive answer, was to go there, to close the distance, to send something across 200 million miles of emptiness and put instruments on the asteroid itself, close enough to touch its surface, close enough to measure its thermal properties directly, close enough to feel the Yarkovsky force rather than merely infer it from distant observations. The mission that would attempt this feat was already being planned. It had been in development for more than a decade, surviving budget cuts, technical setbacks, and the ordinary grinding bureaucracy of government-funded science. Its engineers had designed a spacecraft capable of navigating to a 500-meter target in the trackless void between planets, orbiting it for years, and then performing the most delicate operation in the history of robotic exploration, reaching down to the surface of a spinning, boulder-strewn, almost gravityless rock, and collecting a handful of material that could answer questions about the origin of life and the fate of civilization. The margin for error was measured in centimeters. The distance was measured in hundreds of millions of miles, and the stakes were measured in the survival of cities that do not yet exist, inhabited by people who have not yet been born. OSIRIS-REx was about to launch, and nothing, not the scientists, not the engineers, not even the models, was fully prepared for what it would find when it arrived. Or rather, to send a robot in our place. OSIRIS-REx launched from Cape Canaveral Air Force Station on September 8, 2016, aboard an Atlas V411 rocket. The launch was flawless. The kind of textbook ascent that makes the extraordinary act of hurling a 2,000-kilogram machine into interplanetary spacelook routine. Within 90 minutes, the spacecraft had separated from its upper stage and was on its way, sailing outward from Earth, on a trajectory that would eventually bring it to a rendezvous with a spinning mountain of rubble 200 million miles away. But first it had to come home. OSIRIS-REx was not powerful enough to fly directly to Bennu on a simple transfer orbit. The geometry of the two orbits, Earth's and Bennu's, required a gravity assist, a carefully calculated flyby of Earth itself that would use our planet's gravitational pull as a slingshot to reshape the spacecraft's trajectory and accelerate it toward its target. On September 22, 2017, almost exactly 1 year after launch, OSIRIS-REx swooped past Earth at an altitude of roughly 17,200 kilometers, picking up speed and bending its course toward the asteroid. It was a strange moment, philosophically. A spacecraft built to study an object that might one day threaten Earth was using Earth's own gravity to reach that object. The planet was, in a sense, helping to investigate its own potential executioner. To understand why the investigation was necessary, why we could not simply point a telescope at Bennu and determine whether it would hit us, you need to understand something about the nature of orbits that most people never learn and that many scientists wish were not true. We tend to think of the solar system as a clockwork machine. Planets move in neat ellipses, asteroids follow fixed paths. Everything is predictable if you have enough math. This image comes from Isaac Newton, who showed in the late 1600s that gravity follows precise mathematical laws. If you know the mass of two objects and the distance between them, you can calculate their gravitational pull with perfect accuracy. From that pull, you can determine their orbit forever into the future. It is elegant, it is beautiful, and for two bodies, say the Sun and a single planet, it works perfectly. But here is the problem. The solar system does not contain two bodies, it contains trillions. Every planet pulls on every other planet. Every moon pulls on its host and on its neighbours. Every asteroid is subject to the gravitational influence of Jupiter, by far the dominant perturber, a planet so massive that it contains more material than all the other planets combined, as well as Saturn, Mars, Earth, Venus, and every other massive object in its vicinity. The equations that describe these many-body interactions do not have clean, closed-form solutions. For three or more gravitationally interacting bodies, the problem is fundamentally unsolvable in the classical sense. This is the famous three-body problem, one of the oldest and most stubborn challenges in the history of mathematics and physics. Henri Poincaré, the great French mathematician, proved in the 1890s that the general three-body problem is chaotic, meaning that solutions are exquisitely sensitive to initial conditions and that no finite set of equations can predict the long-term behavior of three mutually gravitating objects with perfect accuracy. For planets, this chaos is usually tamed by the overwhelming dominance of the Sun. The gravitational perturbations from other planets are small relative to the Sun's pull, and planetary orbits remain stable for billions of years. But for a small asteroid like Bennu, the perturbations are not small, not in relative terms. Bennu weighs roughly 78 billion kilograms. That sounds enormous, but it is less than 1/1000th of the Earth's mass and an almost inconceivably tiny fraction of Jupiter's. When Bennu passes close to Earth, or falls under the remote but persistent influence of Jupiter, the gravitational nudges it receives are significant relative to its own orbital energy. A close approach to Earth can shift its trajectory by enough to change subsequent approaches, which in turn change subsequent orbits, and so on, in a compounding chain of perturbations that grows more uncertain with each link. This is the essence of chaotic dynamics as it applies to asteroid orbits. The word chaotic does not mean random. It has a precise mathematical definition. A chaotic system is one where infinitesimally small differences in initial conditions lead to exponentially diverging outcomes over time. Measure Bennu's position today with an accuracy of 1 meter, an extraordinary feat of engineering, and project its orbit forward. After 10 years, the uncertainty in its predicted position might be a few dozen meters. After 50 years, it might be several kilometers. After a century, it could be hundreds or thousands of kilometers. The growth is not linear, it is exponential. Like a snowball rolling downhill, the uncertainty accelerates as it propagates through time, feeding on itself, growing larger with each passing decade. This is exactly the same mathematical phenomenon that limits weather forecasting. Edward Lorenz, the MIT meteorologist, discovered it in the 1960s when he noticed that rerunning a weather simulation with initial conditions that differed by less than 1 part in 1,000 produced wildly different weather patterns after just a few simulated days. He called it the butterfly effect. The notion that a butterfly flapping its wings in Brazil could, through a cascade of amplifying interactions, trigger a tornado in Texas. For weather, the prediction horizon, the time beyond which forecasts become essentially useless, is roughly 10 to 14 days. For asteroid orbits, the prediction horizon is longer, measured in decades or centuries, but the principle is identical. Beyond the horizon, certainty dissolves into probability. Spacecraft arrived at Bennu on December 3, 2018, completing a journey of more than 2 billion kilometers through interplanetary space, and almost immediately, the first surprise landed, a surprise that would force the mission team to rethink everything they had planned, everything they had built, and everything they thought they knew about the surface of a rubble pile asteroid. The mission team had expected a certain kind of surface. Based on ground-based radar observations and thermal models, the prevailing prediction was that Bennu's surface would be relatively smooth, covered in a layer of fine sand and small pebbles, what geologists call regolith. This was not a guess. It was an inference drawn from the best available data. The thermal inertia measurements suggested a surface dominated by fine-grained material. Other asteroids of similar size and composition, notably the asteroid Itokawa, visited by Japan's Hayabusa mission in 2005, had shown mixed terrains with significant areas of fine regolith interspersed with larger boulders. The OSIRIS-REx engineering team had designed the entire sampling mechanism around the assumption that smooth, sandy areas would be available. The sampling device, called TAG-SAM for Touch-and-Go Sample Acquisition Mechanism, was essentially a large circular pogo stick with a nitrogen gas canister. The plan was to descend to a flat area, briefly touch the surface, fire a burst of compressed nitrogen to agitate the loose material, and blow it into the collection chamber, then back away. Simple, elegant, and entirely dependent on finding a flat area large enough and safe enough for the maneuver. When the first high-resolution images arrived from Bennu, the mission team stared at their screens with a mixture of awe and alarm. The surface was not smooth. It was covered in boulders, not scattered boulders, not occasional boulders. The entire surface was a chaotic jumble of rocks, some of them enormous. One boulder near the South Pole was later measured at roughly 70 meters across, taller than a 6-story building. They were everywhere, jutting out at steep angles, crowding every surface, filling every depression. The smooth, sandy landing zones that the mission had been designed for, the zones that the thermal models had predicted, simply did not exist. Dante Loretta, the mission's principal investigator, later described the moment with devastating candor. The word he used was panic. Years of planning, hundreds of millions of dollars in engineering and testing, a spacecraft already at the asteroid with no way to modify its hardware, and the fundamental assumption that the entire sampling strategy was built upon had turned out to be wrong. This was not a minor complication. It was a potential mission-ending crisis. Without a safe landing zone, the spacecraft could not collect a sample. Without a sample, the primary science objective of the mission would fail, and without the detailed surface measurements that the sample would provide, the Yarkovsky effect models would remain less precise than they needed to be, leaving the impact probability stuck in its current haze of uncertainty. But the OSIRIS-REx team did not give up. They adapted. Over the following months, the spacecraft was commanded to perform closer and closer surveys of the surface, mapping every boulder, every shadow, every crevice with centimeter-level resolution. The team developed new software to identify potential landing sites among the rubble, clearings between boulders that might be just barely large enough to accommodate the TAG-SAM head, which was roughly 30 centimeters in diameter. The bar was extraordinarily low. They were not looking for a parking lot. They were looking for a gap between rocks the size of cars that might, if the navigation was perfect, allow a dinner plate-sized device to touch down without striking anything. Eventually, they found 4 candidate sites. After months of detailed analysis, comparing the boulder distribution, the slope, the accessibility, and the spacecraft's ability to navigate to each site with the required precision, the team selected a location they named Nightingale. It was a small depression inside a crater near the asteroid's north pole, roughly 16 meters across, about the size of a large living room. The target zone within Nightingale was even smaller, roughly 8 meters in diameter. To hit it, the spacecraft would have to navigate autonomously through a field of boulders, some of which stood taller than a 2-story building, without real-time guidance from mission control. The communication delay between Earth and Bennu was approximately 16 minutes in each direction. By the time a signal from the spacecraft reached Earth and an engineer's response traveled back, 32 minutes would have elapsed. In that time, the spacecraft could have crashed, bounced, or drifted irretrievably off target. There would be no joystick, no remote pilot, no human hand on the controls. The spacecraft had to do it alone. On October 20, 2020, OSIRIS-REx began its descent toward Nightingale. The maneuver had been rehearsed multiple times, with the spacecraft approaching to within meters of the surface before backing away. But this time was different. This time, it would touch. The descent took roughly 4.5 hours. The spacecraft left its safe orbit and began a slow, controlled fall toward the surface, guided by its onboard navigation cameras and a hazard map programmed with the locations of every known boulder. At an altitude of roughly 125 meters, the spacecraft performed a checkpoint maneuver, a brief engine burn that committed it to the final approach. At 54 meters, it made a matchpoint burn, aligning itself with the rotation of the asteroid so that its descent path matched the motion of the surface below. And then, in the final few meters, the spacecraft's natural feature tracking system, a camera that compared live images of the surface to the programmed hazard map, took control, looking for obstacles and ready to abort if anything unexpected appeared in the landing zone. The tagsam arm extended downward, reaching toward the dark, boulder-strewn surface of Bennu, and at 5:25 in the afternoon, Eastern Time, on October 20th, 2020, it made contact. The touch lasted approximately 6 seconds. In those 6 seconds, the nitrogen gas canister fired, blasting a jet of pressurized gas into the surface. The effect was dramatic. The surface of Bennu erupted. The loose regolith, the fine-grained material that did exist between the boulders, even if there was far less of it than expected, flew upward in a cloud of particles, some of them entering the collection chamber, others spraying outward into space. The tagsam arm sank into the surface, much deeper than expected. The surface was so loosely packed, so lacking in structural integrity, that the arm penetrated nearly half a meter before the spacecraft's thrusters fired to pull it back up. The team watched the footage with a combination of triumph and horror. The sample collection had worked. The chamber was full of material, but the surface response had been startling. Bennu's exterior was not merely soft, it was barely there. Later analysis of the descent footage and the accelerometer data showed that if the spacecraft's thrusters had not fired to arrest its descent, OSIRIS-REx would have continued sinking into the asteroid. The surface offered almost no resistance. One scientist compared it to plunging your hand into a ball pit. Another described it as stepping into quicksand. The asteroid's outermost layer was not a surface in the normal sense of the word. It was a loosely packed suspension of rubble and dust, held in place by forces so weak that a child could have disrupted them. This discovery, that Bennu's surface is essentially a fluid-like aggregate with negligible cohesion, sent shockwaves through the planetary defense community. The implications were immediate and stark. If humanity ever needs to deflect Bennu, to physically push it out of the way of an impact, the method will matter enormously. In September of 2022, NASA conducted a planetary defense test called the DART mission, Double Asteroid Redirection Test. The target was Dimorphos, a small moonlet orbiting the asteroid Didymos. DART slammed into Dimorphos at roughly 6.6 kilometers per second, and the impact successfully changed the moonlet's orbit around Didymos by 33 minutes. It was a triumph, the first time humanity had demonstrably changed the orbit of a celestial body. But Dimorphos is believed to be a largely coherent rubble pile with a more consolidated surface. The DART impact excavated a large amount of material, creating a plume of debris that acted as additional thrust, multiplying the momentum transfer beyond what the impactor alone would have produced. This debris enhancement, the ejector multiplier, as scientists call it, was a critical part of why DART worked so well. For Bennu, the situation could be very different. A kinetic impactor, a heavy spacecraft slammed into the asteroid at high speed, might not produce the same kind of efficient momentum transfer. If the surface is as loose and compliant as OSIRIS-REx's touchdown revealed, the impact energy could be absorbed rather than redirected. Instead of excavating a clean crater and launching a focused plume of debris, the impactor might simply bury itself in the loose material, like a bullet fired into a sandbox. The momentum would still be transferred, but the ejector enhancement could be minimal, making the deflection far less effective than the DART test suggested. Worse still, if the impactor hits too hard or in the wrong place, a rubble pile as loosely bound as Bennu might not deflect at all. It might fragment. Instead of one trackable asteroid on a predictable path, you could end up with dozens or hundreds of smaller pieces, many of them still on an Earth-crossing orbit, all of them harder to track, harder to predict, and collectively just as dangerous as the original object. You would have turned one problem into many, and each of those new problems would be harder to solve than the first. But the boulders and the rubble and the quicksand surface were only part of the story. There was something else happening on Bennu, something no one had ever seen on an asteroid before. Something that made the mission scientists question fundamental assumptions about what these ancient rocks are and how they behave. Bennu was throwing rocks into space. The discovery came in January of 2019, barely a month after the spacecraft arrived. The navigation team, analyzing images taken to track potential natural satellites orbiting Bennu, noticed something strange. Small particles, pebbles really, some only a centimeter across, others as large as 10 centimeters, were being ejected from the asteroid's surface. They appeared as bright dots streaking across the dark background of space in the navigation images. Some of them were moving slowly, just barely above Bennu's escape velocity, drifting away from the asteroid in gentle arcs. Others were slower still, launched upward but not fast enough to escape, rising above the surface and then falling back down under the asteroid's feeble gravity hours, or even days later. A few became temporary satellites, orbiting Bennu for days before either falling back or escaping entirely. The mission team counted more than 300 particle ejection events during the 2 years of close-up observation. Some events launched just a handful of particles. Others sent dozens of fragments flying simultaneously. The largest particles were roughly 10 centimeters across, about the size of a grapefruit. The velocities ranged from a few centimeters per second to several meters per second. By any measure, this was an active surface, a surface that was changing, evolving, shedding material in real time. No one had predicted this. No one had even seriously theorized it. The prevailing view of asteroids, the view held by virtually every planetary scientist before OSIRIS-REx arrived at Bennu, was that asteroids are geologically dead. They are old. They are cold. They have no internal heat source, no tectonic activity, no volcanic processes. They sit in space and do nothing for billions of years, slowly being ground down by micrometeorite impacts and solar radiation, but otherwise inert, unchanging, static on any time scale shorter than geological time. Bennu shattered that assumption. Here was an asteroid actively ejecting material from its surface. Not occasionally, not rarely, but regularly, multiple times per week, in events that were observable from a spacecraft orbiting less than 2 kilometers away. The cause of the ejection events is still debated, and the debate reveals how much we still do not know about the physics of small bodies. The leading hypothesis involves thermal fracturing. Bennu rotates once every 4.3 hours, completing a full day-night cycle in roughly the time it takes to watch 2 feature films. On the sunlit side, the surface temperature reaches roughly 127 degrees Celsius, hot enough to boil water on Earth if there were any atmospheric pressure to hold it in liquid form. On the shadowed side, the temperature plummets to roughly negative 73 degrees Celsius. That is a temperature swing of 200 degrees, twice every 4.3 hours, relentlessly, endlessly, for billions of years. Rocks do not handle this well. The repeated expansion and contraction, heating and cooling, swelling and shrinking, creates stresses within the rock at the grain level. Microcracks form. They propagate. They intersect with other cracks. Over time, the accumulated thermal fatigue weakens the rock from within, and eventually a crack reaches a critical length. The stored elastic energy releases suddenly, and a fragment is ejected from the surface. It is, in essence, a tiny explosion. Not chemical, not volcanic, but mechanical, driven by nothing more than the patient, invisible work of sunlight and shadow. But thermal fracturing may not be the whole story. Some ejection events occurred at locations and times that do not match the thermal model's predictions. Some happened on the night side, where the thermal cycling should be weakest. Some launched up particles at speeds higher than the thermal fracturing model can explain. Alternative hypotheses include meteoroid impacts, tiny space rocks slamming into Bennu's surface at high speed and kicking up debris, and dehydration, in which water molecules trapped in hydrated minerals are slowly released by solar heating, building up gas pressure beneath the surface until the pressure exceeds the strength of the overlying material and a small eruption occurs. There may also be electrostatic effects, the buildup of static charge on the surface by the solar wind and ultraviolet radiation, which could loft small particles off the surface in a process similar to what is believed to occur on the Moon. The The truth is, we do not yet know which of these mechanisms, thermal fracturing, meteoroid impacts, dehydration, electrostatic lofting, or some combination of all four, is responsible for Bennu's particle ejection events. And this uncertainty matters because the ejection of material from an asteroid's surface is not just a curiosity. It is a force. Every particle that leaves Bennu carries momentum with it. The asteroid recoils, infinitesimally, in the opposite direction. If the ejection is asymmetric, if more particles are launched from one hemisphere than the other, or at higher speeds from certain locations, then the net recoil creates a small but cumulative thrust, similar in principle to the Yarkovsky effect, but driven by a completely different mechanism. This mass loss thrust has not yet been incorporated into the orbital models because its magnitude and direction are not well enough constrained. But it exists. It is real. And it adds yet another layer of uncertainty to the already daunting challenge of predicting where Bennu will be in 2182. Meanwhile, the sample that OSIRIS-REx collected, the physical material from Bennu's surface, now stored in a clean laboratory in Houston, has been yielding its own revelations, each one reshaping our understanding of the asteroid and its threat. The sample capsule re-entered Earth's atmosphere on September 24, 2023, after separating from the OSIRIS-REx spacecraft 4 hours earlier at a distance of roughly 102,000 kilometers from Earth. The capsule hit the atmosphere at roughly 12.4 kilometers per second, one of the fastest atmospheric entries of any human-made object, and was subjected to temperatures exceeding 2,800 degrees Celsius as the heat shield bore the brunt of the friction. A drogue parachute deployed at roughly 31 kilometers altitude to slow the descent, followed by a main parachute at 3 kilometers. The capsule touched down gently in the Utah Test and Training Range, a vast expanse of desert west of Salt Lake City, at 8:52 in the morning, Mountain Time. A recovery helicopter reached it within minutes. The canister was transported under strict contamination protocols to NASA's Johnson Space Center in Houston, where a dedicated curation laboratory had been constructed years in advance specifically for this purpose. The lab was maintained at a cleanliness level exceeding that of a surgical operating theater. Every surface was sterilized. The air was filtered to remove particles as small as 1/10 of a micrometer. The scientists who opened the canister wore full-body clean suits, double-gloved, breathing filtered air, operating under nitrogen atmosphere to prevent the sample from reacting with terrestrial oxygen and moisture. What they found exceeded expectations. The canister contained approximately 250 grams of material, far more than the mission's minimum requirement of 60 grams, and enough to supply decades of scientific investigation across laboratories around the world. The material was strikingly dark, nearly black, and fine-grained, with a consistency that one scientist compared to dark, damp sand. Larger fragments, some as big as a centimeter across, were mixed in with the fine material. Every fragment was a relic of the early solar system, unchanged for 4.6 billion years. The most consequential finding for the impact question was the material's physical properties. The porosity of the sample, the fraction of its volume occupied by empty space, was measured at roughly 50%. Half of the material, by volume, was void. This is an extraordinary number. For comparison, typical terrestrial rocks have porosities of 5 to 15%. Even pumice, the volcanic rock famous for being light enough to float on water, has a porosity of roughly 70%. Bennu's surface material sits between ordinary rock and volcanic foam, a sponge of mineral and emptiness, a structure that stores and releases heat in ways that profoundly affect the Yarkovsky calculation. The thermal inertia of the sample material was also measured directly, and it confirmed what the high porosity suggested. The material heats up faster and cools down faster than previous models assumed. This means the thermal lag, the delay between peak solar heating and peak thermal emission that determines the direction and magnitude of the Yarkovsky force, is different from what was plugged into the orbit models before OSIRIS-REx. The correction is not enormous, but it is significant, and it is in the process of being incorporated into the next generation of Bennu orbit predictions, which will produce an updated impact probability. And it gets stranger still. The sample also revealed something about Bennu's internal structure that has implications far beyond the impact question. The density of the sample material, roughly 1.5 grams per cubic centimeter, is lower than any common terrestrial rock. Water has a density of 1 gram per cubic centimeter. Bennu's surface material is only 50% denser than water. And because the bulk density of Bennu as a whole, measured by OSIRIS-REx from the relationship between the asteroid's mass and volume, is roughly 1.2 grams per cubic centimeter, the asteroid as a whole is even less dense than its surface material. This means the interior of Bennu contains even more void space than the surface. The asteroid is not just a rubble pile on its exterior. It is a rubble pile all the way through, a loosely packed aggregate of fragments and voids, held in a tenuous gravitational embrace, with an internal structure closer to a pile of gravel in a jar than to a coherent block of stone. This porosity, this pervasive emptiness at every scale, has consequences that extend to the Yarkovsky effect, the Yorp effect, the structural response to a kinetic impactor, and the long-term fate of the asteroid itself. Because Bennu is not just spinning faster, it is also deforming. The equatorial ridge, that distinctive belt of raised material around the asteroid's midsection that gives it its spinning top shape, is believed to be the result of past spin-up episodes. As the asteroid's rotation accelerated over millions of years, material migrated from the poles toward the equator under the centrifugal effect, building up the ridge. If the Yorp-driven spin-up continues, the ridge will grow, the equatorial regions will become less gravitationally bound, and material will begin to be shed into space. Bennu may, in the distant future, form its own ring system, or spawn a tiny moonlet from its own equatorial debris, or simply fly apart in a slow-motion explosion of rock and dust. But that is a million-year timescale. The urgent question is what happens in the next century and a half. And to answer that question, the scientists need to combine everything: the orbital data from OSIRIS-REx, the sample analysis from Houston, the thermal models, the Yorp spin predictions, the gravitational keyhole maps, the particle ejection data, and the results of future observations, into a single, unified prediction. That prediction will be the most complex orbital calculation ever attempted for any small body in the solar system. It will push the boundaries of computational capability, requiring billions of simulated orbits run on the most powerful supercomputers available. And when it is done, when the next official impact probability number is released, updated with all of the new information, it will represent the best answer that human civilization can produce to the question of whether a half-kilometer rock will hit our planet in the 22nd century. Whether that updated probability will be higher or lower than the current 1 in 2,700 is, as of right now, genuinely unknown. The modeling is complex, involving dozens of coupled physical processes. The data are still being processed in laboratories on 3 continents, and the interactions between porosity, thermal inertia, surface roughness, boulder distribution, and spin state evolution are nonlinear and fiendishly difficult to disentangle. The scientists working on this problem are among the best in the world, applying techniques refined over decades of planetary science. But they are working at the very edge of what current physics and computational capability can deliver. They are trying to predict the future of a chaotic system over a time scale that pushes beyond the mathematical horizon of certainty. And the asteroid, indifferent to equations and anxiety, continues its silent orbit. Every 6 years, it returns to our neighborhood. Every 6 years, Earth's gravity bends its path by a tiny, measurable amount. Every 6 years, the gravitational dice are rolled again, and the uncertainty cloud that defines Bennu's future drifts and shifts and reshapes itself around a set of invisible targets called gravitational keyholes. A gravitational keyhole is one of the most unsettling concepts in all of planetary science. To understand it, think about what happens during a close approach. When Bennu passes near Earth, our planet's gravity bends the asteroid's trajectory, pulling it slightly off course, changing its velocity, reshaping its orbit for all subsequent revolutions around the Sun. The amount of bending depends on how close the pass is. A distant pass produces a tiny deflection, a closer pass produces a larger one, and for any given close approach, there exists a very specific, very narrow corridor of space, sometimes only a few hundred meters wide, through which the asteroid would have to pass in order for Earth's gravity to bend its orbit in precisely the right way to set up a collision on a subsequent orbit. That narrow corridor is the keyhole. It is not a physical object. It is a mathematical region, a set of points in three-dimensional space defined by the equations of orbital mechanics. If the asteroid passes through the keyhole during one close approach, it will be deflected onto a path that leads to an Earth impact during a later close approach, years or decades later. If it misses the keyhole, even by a few hundred meters to one side or the other, the deflection will be different, and no impact will occur on that particular future date. The keyholes for Bennu have been calculated with extraordinary precision. For the 2182 impact scenario, the relevant keyhole is associated with a close approach in 2135. During that flyby, Bennu will pass near Earth, and if it threads the keyhole, a region estimated to be less than 1 kilometer wide, its orbit will be reshaped in exactly the way needed to bring it back on a collision course 47 years later. The 1 in 2,700 probability is, in essence, the probability that Bennu's orbit will carry it through that keyhole in 2135. This framing changes the way we think about the threat. Bennu is not currently aimed at Earth. It is not on a direct collision course. The danger is not that the asteroid is heading straight for us, and we need to push it aside. The danger is that, during a future close approach, Earth's own gravity could redirect the asteroid onto a collision path. The threat is not the asteroid alone. The threat is the asteroid, plus the keyhole, plus our inability to predict with perfect accuracy which side of the keyhole Bennu will pass on. And the keyholes are not static. As Bennu's orbit evolves, influenced by the Yarkovsky effect, by the Yorp spin-up, by the accumulated gravitational perturbations of decades of close approaches, the positions and sizes of the keyholes shift as well. A keyhole that exists for the 2135 close approach might not exist if Bennu's orbit changes between now and then. New keyholes might open for different close approaches. The landscape of risk is not a fixed map, but a fluid, evolving terrain, constantly reshaped by forces that are themselves subject to uncertainty. This is the deep problem of Bennu, and it is a problem that extends far beyond a single asteroid. It is a problem about the limits of human knowledge applied to chaotic systems over long time horizons. It is a problem about what it means to make decisions under irreducible uncertainty. Uncertainty that cannot be eliminated by building better instruments or running faster computers, because it is woven into the mathematical fabric of the system itself. And yet, within that uncertainty, there is also a remarkable achievement. The fact that we can identify the keyholes at all, that we can calculate a meaningful probability for an event more than 150 years in the future, that we can narrow the uncertainty from anywhere in the inner solar system to a cloud of possible positions a few thousand kilometers across. This is an extraordinary triumph of human intelligence and technological capability. A century ago, we did not know that asteroids posed any threat at all. Half a century ago, we could not have detected Bennu, let alone visited it. 2 decades ago, the Yarkovsky effect was still largely unmeasured for individual asteroids. Today, we have a sample of the asteroid's surface sitting in a laboratory in Houston, yielding data that refines our models with every new analysis. The trajectory of human understanding is, in this case, moving in the right direction. We know more about Bennu today than we knew yesterday. We will know more tomorrow than we know today. And each incremental gain in knowledge pushes the uncertainty a little bit smaller, narrows the cloud of possible futures a little bit tighter, and brings us a little bit closer to the definitive answer that everyone wants, and nobody yet has. But here is what makes this truly terrifying. The timeline for gaining that knowledge is measured in decades. The asteroid does not wait for our models to converge. It does not pause while we analyze the sample or refine the thermal inertia measurements or run the next generation of orbital simulations. It simply orbits, and with each orbit, the window for intervention, if intervention is ever needed, grows a little bit narrower. There is a concept in planetary defense called the warning time. the interval between the confirmation of an impact threat and the actual impact date. For Bennu, the nominal warning time is extraordinary by historical standards. We know about this asteroid, we have studied it in detail, we have more than a century and a half before the highest probability impact date. By any measure, we have been given an extraordinary gift of time. Most asteroid impacts in Earth's history, including the one that killed the dinosaurs, came with zero warning. The impactor was not seen, it was not tracked, it simply arrived, announced only by a flash of light and a wall of fire. Bennu has announced itself. It has given us its name, its orbit, its composition, its physical properties. It has allowed us to visit, to touch, to take a piece of it home. It has done everything short of sending us a letter. The question is what we do with this unprecedented advantage. Do we use the time wisely, developing and testing deflection technologies, refining our orbital models, establishing decision frameworks for when and how to act? Or do we do what humans so often do? Acknowledge the risk, express concern, convene committees, publish reports, and then move on to the next news cycle, comforted by the low probability and the distant timeline until the comfortable distance has evaporated and the options have narrowed to desperation? The answer to that question depends on choices that have not yet been made, by people who may not yet appreciate the weight of those choices. And those choices, how seriously we take a low probability, high consequence threat that unfolds over generational timescales, are the subject of the next chapter of this story. But here is what makes this truly terrifying. We are not passive observers of this process. We have the knowledge, the technology, and, if we choose to use it, the capability to change the outcome. The question is not whether we can act. The real question is whether we will act, and when we will start, and whether the answer arrives in time to make a difference. The discovery that Bennu poses a real, if small, threat to Earth did not occur in a vacuum. It landed in the middle of a decades-long conversation among scientists, engineers, military strategists, and politicians about what, if anything, humanity should do to protect itself from asteroid impacts. That conversation has produced 5 distinct approaches to the Bennu problem, each one a chapter in the ongoing story of planetary defense. Some have been tested, some remain theoretical. All of them reveal something profound about the gap between what we can imagine and what we can actually accomplish. The first chapter begins with the simplest and most instinctive response to a rock heading toward your planet. Hit it. The concept is called kinetic impact, and it is exactly what it sounds like. Launch a heavy spacecraft at the asteroid, slam it into the surface at high speed, and use the momentum transfer to nudge the asteroid off course. No explosives, no exotic technology, just mass and velocity, applied with enough force and enough lead time to change the asteroid's orbit by the tiny amount needed to avoid the keyhole. The idea has been discussed in planetary defense circles since the 1960s, but it remained purely theoretical until September 26, 2022, when NASA's DART spacecraft, the Double Asteroid Redirection Test, slammed into the asteroid moonlet Dimorphos at a speed of roughly 6.6 kilometers per second. Dimorphos is a small rubble pile asteroid, approximately 160 meters across, that orbits a larger asteroid called Didymos. Before the impact, Dimorphos completed one orbit around Didymos every 11 hours and 55 minutes. After the impact, the orbital period had changed to 11 hours and 23 minutes, a reduction of 32 minutes. The asteroid's orbit had been measurably, unambiguously, permanently altered by a human-made object. The DART mission was a triumph. It proved, for the first time in history, that kinetic impact can work. The physics is real, the engineering is achievable, and the momentum transfer, amplified by the ejector plume of debris that the impact launched into space, exceeded the minimum predicted value by a factor of roughly 3.6. The debris acted as additional thrust, like the recoil of a shotgun, pushing Dimorphos in the opposite direction even more than the impactor alone would have. But here is the problem. Dimorphos is not Bennu. Dimorphos is roughly 160 meters across. Bennu is 500 meters across, more than 3 times wider. Because mass scales with the cube of the diameter, Bennu is roughly 30 times more massive than Dimorphos. Deflecting an object 30 times more massive requires either 30 times more momentum or 30 times more lead time, or some combination of both, and the surface properties matter enormously. DART's success depended in large part on the ejector enhancement factor, the additional momentum provided by the debris plume. For Dimorphos, the factor was approximately 3.6, meaning the actual momentum transfer was 3.6 times what the impactor alone would have provided. But for Bennu, with its extraordinarily loose, porous, almost fluid-like surface, the ejector enhancement might be much lower. The impactor could sink into the surface material rather than excavating a clean crater. The debris plume could be diffuse rather than focused, and the momentum transfer could fall far short of what DART achieved. Worse still, there is the fragmentation risk. Bennu is a rubble pile held together by gravity and weak cohesive forces. A sufficiently energetic kinetic impact could, instead of deflecting the asteroid as a single unit, break it into multiple fragments. If those fragments remain on similar orbits, which they likely would, since the impact would not change their velocities by much, the result could be worse than the original problem. Instead of one trackable asteroid with a well-characterized orbit, you would have dozens or hundreds of smaller pieces, each one on a slightly different path, each one harder to detect and predict, and each one still carrying enough mass and velocity to cause significant damage upon impact. The DART mission team has been clear about this limitation. Lindley Johnson, NASA's former planetary defense officer, stated publicly that kinetic impact is most effective against smaller, monolithic asteroids, and that rubble piles the size of Bennu may require a different approach, or, at minimum, a much more carefully calibrated impact, with the energy delivered gradually rather than in a single, violent collision. Research groups at Lawrence Livermore National Laboratory and at the Johns Hopkins Applied Physics Laboratory, the institution that built and operated DART, have been studying how kinetic impact performance depends on the target's internal structure. Using hydrodynamic simulations that model the asteroid as a granular medium rather than a solid body, these teams have shown that the eject enhancement factor for a rubble pile can range from less than 1, meaning the rubble actually absorbs momentum rather than amplifying it, to as high as 5 or 6, depending on the impact velocity, the impactor mass, the surface porosity, and the depth of the regolith layer. For Bennu, with its extraordinarily loose surface and high bulk porosity, the simulations suggest an ejector enhancement factor in the range of 1.5 to 3, significantly lower than the 3.6 achieved at Dimorphos. This means that deflecting Bennu via kinetic impact would require a heavier impactor, a faster impact speed, or more lead time than the DART precedent might suggest. There is also the question of where to hit it. The geometry of the impact matters. Striking Bennu at its equator, where the surface material is least gravitationally bound due to the centrifugal effect of the asteroid's rotation, could produce a larger debris plume, but also a higher risk of local fragmentation. Striking at one of the poles, where the gravity is slightly stronger and the surface may be more consolidated, could be safer but less effective. The optimal strategy would require detailed knowledge of Bennu's internal density distribution, knowledge that we currently do not have, and that may require another mission to obtain. Despite these complications, kinetic impact remains the most mature planetary defense technology. It is the only approach that has been tested in space. It is the only approach with flight-proven hardware, and it is the approach that would most likely be attempted first if the decision to deflect Bennu were ever made. One strategy that has gained traction in the planetary defense community is the multiple impactor approach. Rather than launching a single, massive spacecraft and betting everything on one collision, this approach envisions a campaign of smaller impacts delivered over years or decades. Each individual impact would produce only a modest velocity change, perhaps a fraction of a millimeter per second, but the cumulative effect of 5, 10, or 20 impacts, spaced out over the course of a century, could produce a total deflection comparable to a single large impact, with far less risk of catastrophic fragmentation. The multiple impactor strategy has another advantage. Each impact provides new data. The first impactor reveals how Bennu's surface responds to the collision, the actual ejector enhancement factor, the degree of cratering, the momentum transfer efficiency. The second impactor can be calibrated based on those results. The third can be aimed at a different location on the asteroid's surface, testing whether the response varies between the equator and the poles, between boulder-strewn terrain and smoother regolith. Over the course of the campaign, the mission team would build an increasingly detailed model of Bennu's response to impact, allowing each successive impactor to be optimized for maximum effectiveness. This iterative approach transforms kinetic impact from a single, high-stakes gamble into a measured, adaptive program, more engineering campaign than one-shot mission. It requires sustained funding and political commitment over decades, which is its own challenge. But it also provides regular milestones, measurable progress, and tangible results, the kinds of things that keep budgets flowing and public interest engaged. The challenge is not whether kinetic impact works in principle. DART proved that it does. The challenge is whether it works for this particular asteroid, with this particular structure, under these particular conditions. And the honest answer is, we are not sure. This brings us to the second chapter, a concept that sounds like science fiction, but is grounded in remarkably straightforward physics: the gravity tractor. The idea was proposed in 2005 by astronauts Edward Lu and Stanley Love in a paper published in the journal Nature. The concept is elegant in its simplicity. Park a massive spacecraft near the asteroid, not on it, not touching it, just hovering nearby, within a few hundred meters. The gravitational attraction between the spacecraft and the asteroid will create a tiny, persistent pull. By positioning the spacecraft on the correct side of the asteroid and maintaining its position with low-thrust ion engines, the spacecraft acts as a gravitational tug, slowly and gently pulling the asteroid off course. The forces involved are almost unimaginably small. For a spacecraft weighing several tons hovering 300 meters from Bennu's center of mass, the gravitational pull would be measured in micronewtons, millionths of a newton. The resulting acceleration of the asteroid would be so small that it would take years to produce a measurable change in velocity. But the beauty of the gravity tractor is precisely this slowness. Because the force is applied continuously and symmetrically, there is no risk of fragmentation, there is no risk of creating debris, there is no sudden shock to a loosely bound rubble pile. The asteroid is simply guided, molecule by molecule, atom by atom, into a slightly different orbit. The math is striking when you work it out. A gravity tractor spacecraft weighing roughly 10 tons, hovering near Bennu for 20 years, could change the asteroid's velocity by approximately 0.2 millimeters per second. That is a tiny number. But it is applied over decades, and the resulting position change at the time of the keyhole passage could be enough to move Bennu safely to one side. But the gravity tractor has its own problems. It requires an enormous amount of time, decades at minimum, and preferably a century or more. The reason is simple mathematics. The gravitational force between a 10-ton spacecraft and a 78 billion kilogram asteroid, separated by 300 meters, is roughly 1 millinewton. The resulting acceleration of the asteroid is so small that it would take over a decade to produce a velocity change of 1 millimeter per second, and 1 millimeter per second, applied for only 10 years, might not be enough to move Bennu past the keyhole by the required margin. The gravity tractor also requires a spacecraft unlike any that has ever been built. It must carry enough fuel, likely in the form of xenon propellant for ion engines, to maintain station-keeping thrust for years on end, continuously counteracting the gravitational pull that draws it toward the asteroid's surface, while simultaneously pulling the asteroid in the desired direction. The spacecraft must navigate with extraordinary precision, maintaining a fixed distance from a spinning, outgassing, particle-ejecting rubble pile in the microgravity environment of interplanetary space. Any deviation, a thruster misfire, a navigation error, an unexpected particle ejection event from Bennu's surface could disrupt the delicate gravitational tug and require time-consuming corrections. Edward Lu, one of the concept's originators, has been a vocal advocate for developing gravity tractor technology, arguing that its gentleness is precisely what makes it ideal for a rubble pile like Bennu. In interviews and scientific presentations, He has pointed out that the gravity tractor is the only deflection method that treats the asteroid as what it actually is, a fragile, loosely bound collection of debris, rather than as the solid rock that we wish it were. The gravity tractor does not care whether Bennu is solid or fluffy, dense or porous, rocky or sandy. It pulls on the asteroid's center of mass, uniformly and symmetrically, regardless of the surface properties. And it does so without any risk of the catastrophic fragmentation that haunts the kinetic impact and nuclear deflection scenarios. But the gravity tractor requires something that human civilizations are notoriously bad at providing: patience. Multi-decade space missions are technically possible but politically precarious. Governments change, budgets fluctuate, priorities shift. A gravity tractor mission to Bennu would need to be funded, launched, and operated across multiple presidential administrations, multiple congressional sessions, and multiple generations of mission controllers. The spacecraft that begins the mission would be operated, for its final years, by engineers who were not born when it launched. This is not unprecedented in space exploration. The Voyager missions, launched in 1977, are still being monitored nearly 5 decades later. But Voyager is a passive observer, drifting on its own momentum. A gravity tractor would require active, continuous precision operations for its entire mission lifetime. The institutional commitment required is staggering. And in a world where asteroid impacts are perceived as abstract, distant, and unlikely, sustaining that commitment over decades would be an extraordinary challenge. And it requires a level of advanced commitment, political, financial, logistical, that human institutions have historically been reluctant to provide for threats measured in centuries rather than years. The third chapter is the most controversial, the most emotionally charged, and the one that most people think of first when they hear the words asteroid deflection, nuclear deflection. The idea is straightforward on the surface. Detonate a nuclear weapon near the asteroid, not on it, but nearby, close enough that the intense burst of radiation vaporizes a thin layer of the surface. The vaporized material expands outward as a superheated gas, and the reaction force pushes the asteroid in the opposite direction. It is, in effect, a nuclear version of the Yarkovsky effect. A brief, violent, artificial push applied by converting surface material into exhaust. Nuclear deflection has several advantages over kinetic impact for a target like Bennu. First, it delivers vastly more energy per kilogram of payload. A single nuclear device weighing a few hundred kilograms can release energy equivalent to millions of tons of TNT, orders of magnitude more than any kinetic impactor could deliver. This means a nuclear deflection mission could produce a much larger velocity change with a single encounter, potentially deflecting the asteroid with less lead time. Second, because the energy is delivered by radiation rather than by physical collision, the force is applied more evenly across the surface, reducing the risk of fragmentation. The surface layer is ablated, vaporized, over a broad area, creating a more uniform push rather than a localized impact. And yet, nuclear deflection has been the subject of fierce debate within the planetary defense community for decades. The concerns are both practical and political. On the practical side, the physics of nuclear standoff detonation near a rubble pile like Bennu are not well understood. How much surface material would be vaporized? How would the porous, loosely packed regolith respond to intense X-ray and gamma-ray irradiation? Would the ablation be symmetric enough to produce a coherent push? Or would it create chaotic ejector patterns that partially cancel each other out? These questions have been studied theoretically and in computer simulations, but they have never been tested experimentally, for obvious reasons. On the political side, the use of nuclear devices in space is restricted by the Outer Space Treaty of 1967, which prohibits the placement of nuclear weapons in orbit or on celestial bodies. While the treaty does not explicitly address the use of nuclear devices for planetary defense, a scenario its drafters never contemplated, any mission involving a nuclear detonation in space would face enormous diplomatic, legal, and public relations hurdles. The word nuclear carries a weight of fear and suspicion that no amount of scientific reasoning can fully dispel. Even if the physics supported it perfectly, even if it were the only viable option for a short warning time scenario, the political barriers might delay or prevent its use until it was too late. Scientists like Brent Barbee at NASA's Goddard Space Flight Center have studied nuclear deflection scenarios extensively and have argued that nuclear options should be kept on the table specifically for cases where the warning time is short and the asteroid is too large for kinetic impact alone. Barbee's research has involved detailed modeling of what happens when a nuclear device detonates within a few hundred meters of a rubble pile surface. The X-ray pulse from the detonation arrives at the asteroid's surface in microseconds, heating the outermost layer, perhaps a few millimeters to a few centimeters deep, to temperatures of tens of thousands of degrees. This thin shell of material explodes outward as a superheated plasma, and the reaction force drives the asteroid in the opposite direction. The process is analogous to a rocket engine, except the fuel is the asteroid's own surface material and the combustion chamber is the vacuum of space. What makes this approach so powerful is the sheer energy density. A nuclear device weighing 500 kilograms might release energy equivalent to a megaton of TNT, roughly 10 to the power of 15 joules. By comparison, a kinetic impactor weighing several thousand kilograms, traveling at 6 kilometers per second, delivers energy on the order of 10 to the power of 10 joules. The nuclear device provides roughly 100,000 times more energy per kilogram. This enormous energy advantage is what makes nuclear deflection the only option for short warning time scenarios where the asteroid must be moved quickly and decisively. There is a variant of nuclear deflection that has received increasing attention in recent years, the so-called nuclear-enhanced kinetic impactor. Rather than detonating the device near the asteroid's surface, this approach buries or contacts the device against the asteroid and then detonates it, using the nuclear energy not to ablate the surface, but to shatter the asteroid and disperse the fragments widely enough that most of them miss Earth. This approach is considered a last resort, the emergency backup when the impact is imminent and deflection is no longer possible. It is, in essence, the difference between nudging a boulder off a cliff and blowing it to gravel. The first is elegant, the second is desperate, but when the boulder is already falling, desperation is all you have. Researchers at Lawrence Livermore National Laboratory have modeled this scenario extensively using supercomputer simulations that track millions of fragments through their individual orbits over years and decades following the disruption. Their findings are cautiously encouraging. For an asteroid of Bennu's size, a well-placed nuclear disruption could reduce the total impacting mass by 99% or more, converting a civilization-threatening event into a manageable shower of small fragments, most of which would burn up harmlessly in Earth's atmosphere. But the simulations also show that the outcome is exquisitely sensitive to the timing and placement of the detonation. Get it wrong by even a small margin, and you could end up with several large fragments, each one still capable of devastating a city, on trajectories that are harder to predict and impossible to deflect with the remaining time. The moral and psychological dimensions of nuclear deflection deserve attention as well. For many people, the idea of launching nuclear weapons into space evokes images of Cold War escalation, of the arms race extended beyond the atmosphere, of a militarization of the cosmos that humanity has spent decades trying to prevent. These fears are not irrational. The infrastructure required to build, test, and deploy a nuclear deflection system would inevitably overlap with the infrastructure of nuclear weapons. The knowledge gained would be dual use, and the precedent set by detonating a nuclear device in interplanetary space, even for the most benign of reasons, could open doors that are better left closed. But the planetary defense community has increasingly come to accept that ruling out nuclear options entirely would be irresponsible. The universe does not care about human politics. Asteroids do not negotiate, and if a large, fast-moving object is discovered on a collision course with Earth, with only a few years of warning, the nuclear option may be the only option that can save millions of lives. The uncomfortable truth is that the same technology that threatens civilization is also the technology that may one day save it. The challenge is to develop the capability responsibly, to maintain it transparently, and to ensure that the decision to use it is made by the broadest possible consensus of the global community. For Bennu, with its generous warning time and relatively small impact probability, nuclear deflection is not the preferred option. But if the impact probability were to rise dramatically in the coming decades, if new observations or refined Yarkovsky models were to push the odds from 1 in 2,700 to, say, 1 in 50, the calculus would change. And the nuclear option, for all its political baggage, might become the only tool with enough power to solve the problem in time. The fourth chapter of the planetary defense story takes a completely different approach. Instead of pushing the asteroid, it proposes changing the Yarkovsky effect itself, the very force that is nudging Bennu toward the keyhole. The concept is called surface albedo modification. The idea is to change the reflectivity of the asteroid's surface, either by painting it white, literally coating it with a reflective material, or by covering it with a reflective film or scattering reflective particles across the terrain. By increasing the amount of sunlight that is reflected rather than absorbed, you reduce the thermal energy stored in the surface, which changes the thermal emission pattern, which changes the Yarkovsky force, which changes the orbit. It is, in a sense, the most elegant of all the deflection methods. Rather than fighting the Yarkovsky effect, it co-opts it, turning the asteroid's own thermal physics into a tool for self-redirection. The physics is real. The principle is sound. A change in albedo from 4%, Bennu's current value, to say 20%, would significantly alter the thermal emission profile and shift the Yarkovsky acceleration. Over decades, this shift could be enough to move the asteroid away from the keyhole. But the practical challenges are daunting. How do you deliver reflective material to the surface of a rubble pile asteroid with almost no gravity? How do you ensure it sticks to a surface that is already shedding particles into space? How do you coat an object 500 meters across with uniform coverage, including the shadowed interior surfaces of boulders and craters? And how do you do it without inadvertently creating a worse problem? For example, by changing the Yorp torques in a way that spins the asteroid up even faster, potentially breaking it apart. The engineering proposals that have been put forward range from the practical to the fanciful. One approach involves a spacecraft that orbits the asteroid and periodically releases clouds of reflective dust, titanium dioxide, essentially white paint pigment, that settle onto the surface under the extremely weak gravitational pull. Another involves a fleet of small rovers, each carrying a payload of reflective film, that crawl across the surface and unroll strips of material like wallpaper. A third proposal envisions a solar concentrator, a large, lightweight mirror that focuses sunlight onto the asteroid's surface, melting the regolith into a glassy, reflective coating in situ. Each of these concepts has been analysed on paper and found to be theoretically viable, but practically formidable. The dust cloud approach suffers from the problem that Bennu's gravity is so weak that most of the dust would simply drift away into space, rather than settling onto the surface. The rover approach requires navigation and mobility technologies that do not yet exist for rubble pile environments. OSIRIS-REx's experience showed just how treacherous and unpredictable Bennu's surface is, and the solar concentrator approach requires a mirror tens of meters across, deployed in deep space and aimed with precision at a rotating target half a kilometer away, a feat of optical engineering that is far beyond current capabilities. These questions have been explored in academic papers and student design projects, but have never progressed beyond the conceptual stage. Surface albedo modification remains the most creative and the least developed of the deflection options. It is, in the language of technology readiness levels, at the very beginning of the development pipeline, a sketch on a whiteboard promising in theory, unproven in practice. The fifth and final chapter of the deflection story is the one that requires no spacecraft, no nuclear devices, no reflective paint, and no kinetic impactors. It is the approach that humanity is, by default, already implementing. It is called observation, continued, sustained, meticulous observation. And it may be the most important tool we have. The impact probability of 1 in 2,700 is not a fixed, immutable number. It is the output of a model, a model that improves with every new data point. Every time Bennu passes close enough to Earth for radar observations, the orbital uncertainty shrinks. Every year that the asteroid's position is tracked against the stars, the prediction tightens, and as the sample analysis from OSIRIS-REx continues to refine the thermal models, the Diakovsky uncertainty narrows. The most critical upcoming observation window is Bennu's close approach to Earth in 2060. During that flyby, the asteroid will pass within roughly 300,000 kilometers of Earth, close enough for extremely precise radar tracking from ground-based facilities. If the Goldstone or successor radar systems can measure Bennu's position and velocity during the 2060 flyby with sufficient precision, the resulting orbital update could dramatically narrow the uncertainty for the 2135 keyhole passage. It might confirm that Bennu will miss the keyhole by a wide margin, dropping the impact probability to zero. Or it might show that the asteroid is heading closer to the keyhole than current models predict, raising the probability and triggering a more urgent response. In either case, the 2060 observation will be a pivotal moment. It will be the last high-quality radar observation opportunity before the 2135 close approach, and it will likely determine whether the world needs to move from passive observation to active intervention. But observation alone has its limits. It can narrow the uncertainty, but it may not be able to eliminate it entirely. The Yarkovsky effect, the Yorp spin evolution, and the chaotic gravitational perturbations from other planets all introduce irreducible uncertainties that no amount of observation can fully resolve. There may come a point, perhaps after the 2060 flyby, perhaps after additional analysis of the sample data, where the probability is neither zero nor alarming, but simply stuck in a range that is too uncertain to act on and too concerning to ignore. This is the scenario that planetary defense planners find most difficult to prepare for. Not a clear threat that demands immediate action, and not a clear all clear that allows everyone to relax, but a persistent, low-level uncertainty that requires sustained vigilance, continued investment, and the political will to maintain readiness for an event that may never happen. There is a parallel in human experience that captures this dilemma perfectly. It is the problem of flood insurance. People who live in floodplains know that a catastrophic flood might happen in any given year, but the probability is low enough that many choose not to buy insurance. Year after year, the flood does not come, and the decision seems vindicated. And then, one year, it does come, and the people who chose not to prepare discover that the cost of complacency far exceeds the cost of preparation. Bennu is the cosmic equivalent of a 100-year flood, except the probability is measured over centuries rather than decades. The consequences are measured in megatons rather than dollars, and the decision to prepare or not prepare must be made collectively, by a civilization, not individually, by a homeowner. And unlike a flood, which devastates a region and then recedes, an asteroid impact at the energies Bennu could deliver would reshape the environment on a continental or even global scale. The dust lofted into the atmosphere could dim sunlight for months. The thermal pulse from atmospheric re-entry of ejecta could ignite widespread fires. The shockwave, if the impact occurs on land, would flatten everything within tens of kilometers. If it strikes an ocean, which, statistically, is more likely, given that oceans cover roughly 70% of Earth's surface, the resulting tsunami could dwarf anything in recorded history, sending waves tens of meters high cascading across coastlines thousands of kilometers from the impact point. These are not speculative doomsday scenarios. They are the outputs of validated impact physics models, developed by institutions like Los Alamos National Laboratory and the Sandia National Laboratories, and calibrated against the geological record of past impacts. The asteroid that created the Chicxulub crater 66 million years ago and ended the age of the dinosaurs was roughly 10 to 15 kilometers across, 20 to 30 times Bennu's diameter. Bennu would not cause a mass extinction, but it would cause devastation on a scale that no living human has ever witnessed and that no human infrastructure has ever been designed to withstand. The question, then, is not whether Bennu deserves attention. It does. The question is whether human civilization is capable of sustaining that attention across the timescales required. the asteroid will not arrive for more than a century and a half. The people who will need to respond to the final determination of whether Bennu will hit Earth have not been born. Their grandparents may not have been born. The institutional memory required to maintain vigilance across such timescales exceeds anything human civilization has ever achieved, and the OSIRIS-REx spacecraft itself has a role to play in the next chapter. After delivering the sample capsule to Earth in 2023, the spacecraft did not shut down. It was in excellent health, with fuel to spare, and NASA repurposed it for a new mission, OSIRIS-APEX, which stands for OSIRIS-APOPHIS Explorer. The spacecraft is now en route to the asteroid Apophis, another potentially hazardous near-Earth object that will make an extraordinarily close approach to Earth on April 13, 2029, passing within roughly 32,000 kilometers of Earth's surface, closer than many geostationary communications satellites. Apophis is roughly 340 meters across, smaller than Bennu, but still large enough to cause devastating regional damage in the event of an impact. When it was first discovered in 2004, initial calculations gave it a disturbingly high impact probability, at one point estimated at nearly 3% for a 2029 impact. Subsequent observations eliminated the 2029 threat and later eliminated a 2036 impact scenario as well. Apophis is now considered safe for at least the next century. But the OSIRIS-APEX mission will study Apophis during and after the 2029 close approach, watching how Earth's gravity deforms the asteroid's surface, changes its spin state, and alters its orbit. The data will be invaluable for understanding how close approaches affect rubble pile asteroids, the exact physics that governs Bennu's key holes. The connection between Apophis and Bennu is not coincidental. Every observation of a near-Earth asteroid, every mission that visits one, every measurement that refines our understanding of surface properties and orbital dynamics contributes to the broader effort to protect Earth from impacts. The knowledge is transferable, the techniques are shared, and the timeline is long enough that lessons learned from Apophis in 2029 can inform decisions about Bennu in 2060 and beyond. This interconnected web of observations, missions, and analyses represents something new in human history, the emergence of a genuine planetary defense infrastructure. It is not housed in a single building or commanded by a single authority. It is distributed across dozens of institutions and half a dozen countries. NASA's Planetary Defense Coordination Office, established in 2016, coordinates the American side of the effort. The European Space Agency operates its own Planetary Defense Office and is developing the Hera mission to revisit the Didymos system and study the aftermath of the DART impact in detail. The International Asteroid Warning Network, operating under the auspices of the United Nations, provides a framework for sharing observations and coordinating responses across national boundaries. But the infrastructure is fragile, funding is modest. NASA's entire planetary defense budget is a fraction of 1% of the agency's total spending. The telescopes that survey the sky for near-Earth objects are aging. The radar facilities that provide the most precise orbital measurements are few in number and oversubscribed, and the political attention devoted to asteroid threats waxes and wanes with the news cycle. In the weeks after a spectacular meteor event, like the Chelyabinsk airburst over Russia in 2013, when a roughly 20-meter asteroid exploded in the atmosphere with the force of 500 kilotons, injuring over 1,000 people and damaging thousands of buildings, funding and attention spike. Then, inevitably, they fade. The challenge of sustaining a planetary defense program across decades and centuries is in many ways harder than the engineering challenge of deflecting an asteroid. Engineers know how to build spacecraft. Physicists understand the orbital mechanics. But no human institution has ever successfully maintained a focused, well-funded program against a low-probability, long-term threat for more than a generation or two. The closest analogues, nuclear deterrence, flood control, earthquake preparedness, all show the same pattern: initial urgency, gradual complacency, and then, when the disaster finally arrives, a frantic scramble to rebuild what was allowed to decay. But the clock is ticking, not loudly, not urgently, but steadily. The orbital mechanics do not wait for committee reports or budget cycles. Every year that passes without a decision about Bennu's deflection, if deflection is ever needed, is a year that narrows the window of opportunity. Deflecting an asteroid by kilometer requires far less energy if the deflection is applied a century before the impact than if it is applied a decade before. The relationship is roughly quadratic. The deflection needed scales with the square of the remaining time. Wait until the last decade, and the energy required to avoid impact increases by a factor of 100 or more. This is the terrible arithmetic of planetary defense. Time is the most valuable resource, and it is the one resource that is constantly being spent. Every day of delay makes the eventual solution harder, more expensive, more uncertain, and more desperate. The people who will face the consequences of today's inaction have not been born yet. The people making the decisions today will not live to see the results, and the asteroid, indifferent to politics, budgets, elections, and the short-time horizons of human institutions, continues its orbit, patient, silent, and bound by nothing but the laws of physics. And this raises a question that is not technical but profoundly human. Who decides? If the impact probability rises to the point where active deflection becomes necessary, who makes the call? There is no international body with the authority to order an asteroid deflection mission. The United Nations Committee on the Peaceful Uses of Outer Space has discussed the issue and produced recommendations. But recommendations are not mandates. Individual spacefaring nations, the United States, China, Russia, the European Consortium, Japan, India, each have their own space agencies, their own budgets, their own political pressures, and their own strategic interests. A decision to deflect an asteroid is, at its core, a decision to change the trajectory of a natural object in the solar system, to alter the gravitational environment in ways that could, in principle, shift the risk from one country or region to another. Consider the scenario. A kinetic impactor is launched to deflect Bennu. The impact is partially successful. It changes the asteroid's trajectory enough to avoid the primary keyhole, but, due to uncertainties in the momentum transfer, pushes the asteroid toward a different keyhole that leads to a different potential impact point. The original impact would have struck the Atlantic Ocean. The new trajectory threatens a land impact in Central Asia. Who bears the responsibility? Who consented? The mathematics of orbital deflection is precise, but the politics of who gets to move a mountain through space is anything but. These governance questions are being discussed today in academic conferences and diplomatic working groups by people who understand that the technical capability to deflect an asteroid may arrive before the political framework to use it responsibly. The Space Mission Planning Advisory Group, formed under United Nations auspices, has developed theoretical response plans and conducted tabletop exercises, simulations where international teams practice responding to a hypothetical asteroid threat. These exercises have been remarkably revealing. They consistently show that the technical decisions, what kind of mission to launch, how much lead time is needed, what trajectory to use, are the easy part. The hard part is the human decisions. Who funds the mission? Who builds it? Who launches it? Who decides whether the risk is high enough to justify action? And who takes responsibility if something goes wrong? For Bennu, these questions are not abstract. They are the questions that will need to be answered, perhaps by the middle of this century, perhaps later, but eventually, if the impact probability does not drop to zero. And the answers will depend not just on science and engineering, but on trust. Trust between nations, trust between institutions, trust between generations, and trust in the ability of human civilization to act collectively in the face of a threat that is real but distant, certain in its physics but uncertain in its probability. The 5 approaches to deflecting Bennu: kinetic impact, gravity tractor, nuclear deflection, surface albedo modification, and continued observation, are not mutually exclusive. The most likely response, if a response is ever needed, will involve a combination of strategies deployed in sequence over decades. Perhaps early kinetic impact tests to demonstrate capability and refine models, followed by a gravity tractor mission to provide precise, long-duration course corrections, with a nuclear deflection system held in reserve as a failsafe. Perhaps improved observation campaigns in the near term, feeding data into increasingly sophisticated simulations, buying time for technology development that has not yet been imagined. The history of technology suggests that the tools available in 2100 will be as different from today's tools as today's tools are from those of 1900. A civilization that can build starships may find asteroid deflection trivially easy. Civilization that has mastered nanotechnology may be able to disassemble an asteroid atom by atom. These possibilities are speculative, but they are worth noting because the timeline of the Bennu threat extends far enough into the future that today's technology is not necessarily the technology that will be used. What is needed now, in the first decades of the problem's existence as a known threat, is not a solution. It is the foundation for a solution. Better observations, better models, better technology development, better international coordination, and above all, better communication between scientists who understand the risk, policymakers who control the resources, and the public who will ultimately bear the consequences. There is a moment in every documentary about an asteroid threat, every news segment, every press conference, every headline, where the storyteller steps back from the science and asks the question that is really on everyone's mind: should we be afraid? The answer, in the case of Bennu, is both simpler and more complicated than it seems. The simple version is no, not today, not tomorrow, not for at least 100 years, and probably not ever. The impact probability is 1 in 2,700. That means there is a 99.963% chance that Bennu will miss Earth entirely. If you were given odds of 99.963% on anything else in your life, that your flight will land safely, that your surgery will go well, that your house will not burn down tonight, you would sleep soundly. You would not lie awake, staring at the ceiling. You would not cancel your plans or rewrite your will. You would simply live your life and trust, quite reasonably, in the overwhelming likelihood that everything will be fine. But the complicated version of the answer is that probability alone does not capture the full picture. A 1 in 2,700 chance of a catastrophe is different from a 1 in 2,700 chance of a minor inconvenience. The magnitude of the consequences matters. A coin flip is a 50-50 proposition, and we make casual bets on it all the time. But if someone offered you a coin flip where heads meant you win $1 and tails meant the destruction of a city, you would not take the bet. Not because the probability is high, but because the downside is too catastrophic to accept at any probability. This is the essence of what risk analysts call expected value, and it transforms the Bennu problem from a reassuring statistical curiosity into something more sobering. The expected value of a risk is the probability of the event multiplied by the magnitude of its consequences. The probability is small, but the consequences: 1,200 megatons of energy released upon impact, a crater 5 kilometers across, tsunamis reaching across ocean basins, dust and debris darkening the sky, fires igniting across continents, are so enormous that even a tiny probability produces a significant expected cost. It is the same logic that drives us to buy insurance for events we do not expect to happen. The premium is small. The potential payout is life-altering. And the act of preparing does not mean we believe the worst will come, only that we recognize the cost of being wrong. Bennu is an insurance problem on a civilizational scale, and the question is not whether the premium is worth paying. It almost certainly is, but whether human civilization is capable of paying it. Because the premium in this case is not money, it is attention. Sustained, patient, multi-generational attention, the kind that human institutions are least equipped to provide.